I'm Ali, and I'm going to talk about live migration of virtual machines along with their storage over wide area networks. So today, right, we like to think that virtual machines provide this really nice container where you can just move things around, and we call this process live migration. It would be really nice if it just works as simple as I just demonstrate here, and it exists in this magical place called the cloud. But And with that, we can build a lot of nice benefits, right? We can use it for a lot of applications, right? There's test to production data center migration. There's the disaster preparedness testing, which is mandated by a lot of governments now. There's also crust data center load balancing, which surprisingly a lot of our customers are interested in. And these shared nothing architectures that are becoming increasingly common in modern applications. But unfortunately, the picture is a little more complicated. So one, you have to have some shared storage so that the virtual disk is available on the source and destination. And you iteratively copy memory, using up a lot of network bandwidth. And finally, when the VM's really close to having everything copied over, you stop the VM, migrate over its virtual device state, and resume it on the destination. So this puts a few requirements on our system. One is that we have shared storage. Second is to have fast networking. And lastly is you want the VM to exist on a single subnet. Well, this really isn't what we want. We'd like to eliminate these problems. So there's a handful of technological changes that are driving these use cases and the solutions to them. So one is the shared nothing application architectures. Right here, a lot of customers basically don't want to use SANs because they're expensive and they're extra maintenance overhead. They would like to just use the local disk attached to their boxes. Next is all these network mobility protocols that are out there to help with that, which are like Lisp and OTV, and network virtualization solutions like VXLAN and OpenFlow make it possible to migrate applications between data centers. We're not going to talk about that in this talk, but you can see the references in the paper and go look up, and they are being used, though, with XvMotion. I'm just going to gloss over them. The last thing is that our customers have very large data centers, and they have multiple of them. So they have 3, 4, maybe even more data centers with thousands of physical hosts that are running lots of VMs on each one. So there's no reason for these limitations, and all these new use cases are being desired by our customers. So this brings us to basically what XvMotion is. This is the first commercially viable WAN migration solution. We achieve low downtime and an atomic switchover, and we use asynchronous I/O mirroring to take care of the storage aspect. And our basic principle that we're going to focus on in today's talk is the flow control mechanisms used by XvMotion in order to allow memory and disk copy to be completed successfully with good performance and low overhead. So what do customer scenarios look like? Well, on the local area networks, customers have very fast networks. They've got 10 gigabit, sometimes even 40 gigabit we're seeing, and they actually dedicate network bandwidth just to migration. So it's not uncommon to see customers who have several 10 gig NICs that are dedicated just for migrating a very large VM between a handful of hosts to provide all the functionality that they'd like to see. And the latencies on these networks are extremely low, in the order of a millisecond or less. On the wide area, though, the story is very different. Seeing a gigabit of bandwidth is probably about what we expect to see with most of our customers that they're willing to give us for a wide area migration. You're going to see hundreds of milliseconds of latency. So imagine from California to India, that's about 200 milliseconds of latency. And there's also going to be a lot of other applications sharing this connectivity. So there'll be packet loss, there's going to be unreliable throughput. And this leads us to what are the kinds of customers or applications that we care about? Well, virtualization has a lot of legacy applications that still run in it. These applications are, multi-tier still. They have a client, they have some application, and some kind of database that stores the data. In this example, I wanted to illustrate an important point is I'm pointing out a highly available database. So high available applications have some kind of timeouts, and these timeouts are on the order of seconds typically. So this brings us to our first critical goal of XvMotion, which is what we call downtime. So downtime is this concept that when you do a migration, at some point you will stop execution on the source, you will migrate over any remaining state, and you will resume execution on the destination. And this this little pause in time is externally visible to other applications. So for HA applications, they're looking on the order of seconds, so our goal should always be below that. So we target less than a second of downtime. Our next important goal is what's called atomicity. And these are sort of competing goals, as we'll see in the next section. And what's going on here is that imagine that you migrate over your memory state and your execution context to the other host. But your disk remains on the source, and you're going over a wide area network to access your disk. So not to mention there's some performance issues going on, but there's also this issue that if the network goes down, there's a network partition, then you have no other choice but to kill the VM on the destination, and the customer has to come in and restart the VM. It's essentially like pulling the plug on a host. You might have to recover the file system. You might have a lot of other things to deal with that are going to lead to minutes or hours of downtime. And this is really undesirable for a lot of these enterprise workloads. So XvMotion unifies our memory migration and storage migration techniques so that we can tolerate wide area networks in terms of bandwidth and latency, and also in terms of reliability issues like packet loss and throughput instability. We tolerate heterogeneous storage performance, and we also want to give a goal of downtimes and workload impact comparable to local area migrations. And finally, our primary goal is an atomic switchover, so that you can really be confident that XvMotion is safe for customers. Today, this is already deployed in metro area networks, and some of the stuff I'm talking about to deal with latency are currently being developed, and we hope to deploy that later. So let's get started with some architecture overview. So unified live migration, or XvMotion, essentially works by establishing an I/O mirror for the virtual disk. We copy the disk over and start mirroring I/Os to the destination host, and then we'll do a normal memory migration and copy over the device state. But we've tied these together so that in a single successive step, we'll actually do the final switchover from source to destination. So there's no cross-dependence. The architecture diagram is fairly simple. Essentially, the virtual machine issues its I/Os now into what we intercept with an I/O mirror filter driver that will take the I/Os, write them out to the source disk, and also copy them into an I/O buffer on the source. The virtual machine, the live migration module, takes care of orchestrating the memory pre-copy and also the device state transfer, and also deciding when the migration ends, sort of monitoring the progress of both processes and deciding convergence. And lastly, what I show here is the streams framework, which is, we're not going to talk about here. You can see in the paper for more details. This is basically a framework for transporting bulk data, and it's designed to optimize for CPU, for local area networks where you have tons of bandwidth, and also designed to optimize for latency when we have wide area networks, and it takes care of dealing with all those configurations. On the destination, we also have a writer process, which is responsible for writing out data to the disk. So today I'm going to focus a little bit on some of the wide area migration issues when it comes to memory and storage. So let's talk about memory. And then this is basically focusing on the live migration modules that I showed in the previous diagram. So when you look at memory, you have all this data you need to copy over to the destination. Well, you can mark it all dirty and say, okay, I need to copy all this all over to the destination, and I'll just copy it over. And during the time it took me to copy all of the system's memory, some stuff changed on the source. So I'm going to copy that over. And I'm going to continue to do this in successive iterations. And my goal is that in each iteration, I'm going to copy less and less information until finally I can stop the VM, do the final copy, and resume on the destination. This depends on the network being faster than the application's dirty rate. Now, a solution that is being used by multiple hypervisors is to resume early. And what this means is that because applications can often write memory much faster than the network, this is sort of fundamental due to like the hardware, we stop the migration when we decide we're not making any more progress in copying, and we resume on the destination early. Now that means there's still memory on the source you haven't copied over. So you start executing on the destination, and you will take remote page faults all the way to the source to retrieve any pages you're missing, and at the same time in the background, you'll push over the remaining data, so 20, 30 seconds later, you'll have all of memory on your destination, and your VM is no longer dependent on the source. This brings us two important problems that exist with this current solution. And the first is that remote page faults are really expensive over wide area networks. So imagine from our California to India use case, you have 200 milliseconds of latency every time you take a page fault. 5 page faults in, you've already have an extra second of downtime. So effectively, your application's not making progress. It's not doing anything. And these are the hottest pages typically, so the penalty is really, really bad. And the next important thing is that this is not atomic. It's unsafe to do this over a wide area network. So our solution to this is to throttle the VM just enough to keep the dirty rate below the network rate. And we do this by injecting small millisecond sleeps into basically our page fault handler when we see pages being modified for the first time. So here are some of the results of our SDPS technique. So when SDPS is off, we see that the virtual machine, basically in terms of performance, when a workload scales, you'll see downtime scales sort of proportionally. We have a 24 user workload and a 48 user workload on this DVD store workload. And what's going on here is downtime increases. Now you're up to 2 seconds of downtime when you have 48 users. But when SDPS is turned on, this stun feature basically allows us to slow down the workload gradually and allow the downtime to be constant. So there's a little bit of variability. We've targeted half a second of downtime here, and the delta you see on top is basically due to the device checkpointing and resuming. So now let's talk about like how wide area storage migration is done. So here you have an I/O mirror, filter driver, we're going to talk about that. We're going to talk about some of the buffering and also how the writing is done on the destination. So there's 2 major issues I'm going to talk about today. The first is that synchronous mirroring over the WAN slows down the guest workload, and it's really not practical. As I mentioned, imagine 200 milliseconds of latency for every time you write to your disk. Your local disk is going to be no more than about 5 to 10 milliseconds of latency, and an SSD would be much faster than that. So we want to hide this latency. So the simple solution is to do asynchronous I/O mirroring. So I/Os are written to the source disk and also to an I/O buffer. And at the same time, we'll also do our bulk disk copy from start to finish of the disk. We'll copy it into the I/O buffer. And chunks of the buffer, as they fill up, will be transmitted to the destination with the streams framework and eventually written out to the destination disk. But this leads to another problem. Now, what if the workload's too fast on the source for the destination? So we need to somehow have a mechanism to throttle the copy process. So what we did is we introduced our own congestion control. Imagine that you have this slow disk on the destination that's running at half the rate. What you do is you want to introduce back pressure onto the source. And we do this with 2 features. The first is that we limit the amount of buffer space on the destination, and then we send the amount of free buffer space that's available to the source. This functions a lot like TCP congestion control. We do this actually on a per disk basis, so this generalizes very well to multiple disks and help deal with fairness issues across multiple disks as well. So now when things happen, we'll see that the source will slow down to the destination speed. So now let's take a look at how the end-to-end system sort of works. So I'm going to evaluate things in terms of 3 important metrics. The first is migration time. This is the time from when I start the migration until when I end the migration. The next is downtime. As I mentioned before, this is the time from the last instruction executed on the source until the first instruction is executed of the VM on the destination. And then the last thing is workload penalty. And think of it as the average penalty to the virtual machine during the migration. All the tests here are going to be done with an OLTP I/O workload. We'll do it to a data disk only, which is about 12 gigabytes, and we're also migrating a system disk that's mostly idle. So here you're taking a look at downtimes, and what you see, things are pretty much constant. We have approximately a second of downtime from 0 milliseconds to 200 milliseconds, which is enough to go around the globe. The important thing to take away here is that our convergence algorithm that decides when the migration stops is able to use SDPS, our stun during page send, which slows down the VM's execution, and also use the congestion control on our storage to sort of manage how much data it'll actually have to copy during the downtime and target that 1 second downtime. That's why we're able to achieve pretty good consistency. There's some synchronous RPCs that'll affect us as we go past 300 milliseconds, but those aren't, we didn't get to measure those. The next is migration time. And what you see here is a small linear time increase as the latency increases. And this is to be expected because you have TCP slow start that occurs several times as various TCP sockets are warmed up for the cross vMotion to occur. And that sort of has this exponential curve of how it ramps up, and you're going to expect a little bit of increase in total time. But the bulk of the copy, remember that VMs are so large that when you're copying for tens of minutes or hours, it doesn't really matter that your ramp up was in the first 20, 30 seconds and how much change was there. And lastly, I wanted to mention our California to India migrations that we've been doing as a test. So these were done also on a gigabit network with about 214 milliseconds of round trip time. And with the OLTP workload, we were able to saturate the network during the memory copy at 89 megabytes a second and use about 68 megabytes a second during disk copy. There we were bottlenecked by our disks. And the last important thing is that the workload penalty, the average penalty to the VM, to the actual throughput, was only 11%. And this didn't matter whether we were in the local case, just migrating with 0 milliseconds of latency, 2 machines next to each other, or we were migrating all the way to India. It had latency had no impact on workload impact. So in summary, cross vMotion frees migration from the need for shared storage and these fast local networks. We can tolerate wide area network bandwidth, latency, and also there's reliability issues. We can tolerate heterogeneous storage performance, and we can guarantee an atomic switchover along with low downtimes because of the way we can throttle the VM. The downtimes and workload penalty, as I mentioned, are comparable to local area migrations. And finally, we give this atomic switchover, which is a very critical feature to making XvMotion safe. This enables a lot of new use cases, as I mentioned, disaster recovery, cluster upgrade, and all these shared nothing architectures. And we're on the path to deployment. As I mentioned, we've already been using this for a little over a year on metro area networks, and it's been in development for several years at this point. Questions?
Yeah, Charlie Johnson, HP Labs. When you're migrating to the new site and you're in the process of doing it, do you have any way of, if there's a problem on the new site where something doesn't fit or there's not enough capacity or whatever, that you can fail back? Or is it basically, if something's wrong, you end up nowhere?
So in terms of like resource constraints, VMware generally reserves resources on the destination before the migration starts, so we guarantee we have enough memory and so forth.
That's not my question.
You mean in terms of failures?
In other words, if there's something wrong on the other side, whatever it is, do you end up nowhere if there's...
No, we fail back to the source.
You fail back.
Until that switchover point at the very end, you will fail back to the source if there's any kind of failure.
Hi, Fred Douglas, EMC. Oh, this side.
Yeah.
So it seems like everybody who's been doing VM migration sort of reset the clock in the early 2000s and forgot about everything that had been done before that. So I looked at your paper, and I think that it's only appropriate to consider that somebody at your own institution, Stanford, did the pre-copying and and the idea of keep sending and then wait until things stop changing long enough 20 years ago, and unless or yeah.
I mean,
so so Marvin Timer has done the pre-copying.
I'm not claiming pre-copy is anything new here. As I said, pre-copy and even the early resume, what we call like post-copy, is all prior work that's been researched.
Right. So what I'm saying is that I think that should give the appropriate credit to the pre-copying work, and the pre-copying work didn't start in 5 years ago or whatever with the VM work. Is all I'm saying.
See.
So I think that the idea of stunning it to sort of pace the pre-copying is an interesting addition beyond that.
Yeah.
But I think that it does deserve homage to the right people.